fucking link. Okay, it says it's live. And it is playing this time. Hooray. Okay, so it is live this time. So now I have to get the link. And I have to send it to Michael. Copy, close. Let's see if I can do this with reasonable efficiency. Maybe possible. I did seem to get it right, so this system I have here should work. If we're lucky, I paste the link there, and then I post it as a link, and that should give me a link. And I say yes to that, and then I just pop over here. What the hell did it do? Google Hangouts. I don't know what it did to my link. Copy, timestamp, edit. No, I don't want to do any of that shit. Fuck you. I don't know why. I don't know. Skype didn't even post the link properly, I don't think, but who knows. All right. Now I should be able to refresh this, and there should be my link right there. I should just copy the link and go back to Skype. Go back to Skype. Hello. No, I'm not saying hello to you. You don't say hello. Paste. That should be the link. Well, let's see if it works. And such. It looks correct. I mean, from what I can see of it before they turn it into a stupid goddamn fucking video, which I don't understand. I don't know why they just don't give you the link. I posted it as a link, as text. I don't know why they got to convert it into a thing. I wonder if I can get this microphone in a better position. I wonder what happens if I click on it on Skype. Well, I might as well just try it for fun. And I'll do it in Chrome just to make life more interesting. Probably won't let me in because I won't have an account on the Android, I don't think. Yeah, totally crashed. Brilliant. Let me see. No, it didn't crash. Why did it open it again for? I don't know. That's just really fucking putridly stupid. Oh, it did crash. Okay, it just wouldn't admit that it crashed. All right, anyway, let's see how Michael does, if he gets in or not. I'll have to think of some other way to send a link rather than sending it as a link. I don't know. Ah, there, he made it. So it did work. Amazing. All right, so at least I figured that part out. Let's see. Can I hear you?
Can you hear me?
Whoa. I think I heard too much. Try again. Hello. Hello. Do a test. Hello. Testing. 1, 2, 3.
Hello.
Okay, that's enough of that.
G'day, Mike.
Yeah.
Is that better?
Don't try any of that freaking Australian psychology crap on me.
Throw another shrimp on the barbie.
Yeah, yeah, you really have been kind of pwned by your own commercialism.
Oh, that's
yeah, well, it's I don't know. I had some trouble even making the room, so I don't know what's going on exactly. But
hang on a sec.
Yeah.
So just to let you know, I obviously received your link in Skype and it puts a little icon there, but what I did is I right-clicked it and it gives you the option to copy link.
Yeah, I don't know how I don't know why they're doing that. I mean, Skype is kind of retarded. I mean, you know, why would it turn the link into a YouTube video? Because it's a Google thing, and I don't know. But anyway, so I don't know how I'm supposed to, I guess if I take the HTTP off of it or something, then they won't consider it a link, and then you can just copy the text, and, you know, you still have to type it in the browser. I mean, pop it in the browser, but yeah, it's just irritating. I don't know why they turn the links into that. Well, anyway, you figured it out, so it doesn't matter, but just thinking for future purposes. I'll have to think of maybe if I just put the link in brackets or something, then they won't linkify it.
Just delete the HTTPS off the front of the link. But when I kept clicking it, it kept defaulting to open Firefox, so I had to just right-click it, get the link, and paste it into Opera.
Yeah, well, I tried it myself just to see what would happen, and I opened it in Chrome, and it crashed. Yeah, Google makes Chrome, right? I mean, that's just kind of funny, right? Chrome crashed opening the room. So, I'll just try it again just for fun. Let's just see what happens. Let's see if I can get into the room. Because I don't think I'm signed in on Chrome. Yeah, it crashed again. That's hilarious. Yeah, it just crashes. So anyway,
I've been drawing a lot of diagrams. I hope you're not offended, but I've got quantoritis.
Yeah. Oh, good. Yeah, I don't think I had any real agenda. I mean, I was going to do a room earlier, and I just said, nah, I don't got enough energy, and I don't have enough to say, and blah 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 blah. But I've just been thinking about the just still trying to diagram exactly how once the shit is inside of like an electron, the polarization, theoretically it all has to be, it's got to be the same pressure as the outside pressure in a sense. You know what I mean? There's just as many density of arrows on the outside of an electron as there are density of arrows on the inside. And all you're really talking about is somehow there's been an orientation trap, where because of this polarization thing, they keep bouncing back and forth, And so I was just thinking about that mechanism and the fact that, when I make this argument that the different polarizations bounce off and you can see the difference in the universe, you know what I mean? The reflection is more obvious when there are two different colors, so to speak. When I made the blue versus the blue-red interaction, right? It makes it more obvious that there was an interaction. But I was saying theoretically, it's still exactly the same thing is happening. Something's reflecting off of another thing. And so anyway, so I figured out what it's just sort of interesting. Like when it encounters polarization of the same polarization, like say if I sent one extra blue arrow towards an electron, and the electron's the blue, what it's kind of doing is it's absorbing the reflected arrow. So when the blue first reflects, it's like the electron, that becomes part of the electron, that new blue, because it's the right color. You know what I mean? It's like you can't tell it from the electron, because it's now an addition to the electron. So it's really theoretically doing the same thing. It's bouncing off the field energy again, and then going the right direction. So first it goes a little bit the wrong way, and then it goes the right way, when it gets reflected, in the sense that that's the new addition way. Well, anyway, so it's just it's kind of subtle, and I was just surprised how very subtle all this stuff gets. These little subtle interactions, and you have to be so careful in dissecting them, because you miss one little thing, and the whole thing blows up. The whole thing fails, if you don't recognize the little subtleties. So anyway, that's
that's hopefully that's what the benefits of having a conversation with someone about this subject for you will bring to you, because I've got a lot of questions for you.
Okay.
And I understand now why it's so difficult for you to me and tell others, because even trying to diagram it and think about a model, I got some modeling software free the other day, and I downloaded, and this is really hard to put in a model, so I can understand why you haven't to date, because it'd take for ages, and it is pretty hard, and especially if you don't have access to modeling software and being sort of fluent in using it, it would be very difficult. But I've been waiting for you obviously to come on for a few days. I'm glad you have. Thanks for responding on Skype. I just want to show you some diagrams.
Fine.
Yep. If when you see them, I'm just going to flip through them. There's about 10, but at least you'll probably know that I'm starting to understand what you're saying. But so I'll show you where I started, and I'll just progress through them. So just as a bit of a joke, here's a hyperboloid fish perturbation.
Yeah. Well, that's yeah, not terribly useful, but it's good you added. Now you've added some rationality to it, though. At least now I
Yeah,
can
have a look.
I'm starting to get it now. I'm getting the hyperboloid now because the fish makes sense to me now. So it all
Have a
fits.
look. But in all seriousness, have a look in the center of the diagram, because I know what you're talking about, fish suits now. So
Yeah.
that's actually fish shedding their skin and the skeletons popping out the other side.
Ah, very good. Yes, very good.
So so I've got your problem now. I'm starting to draw stuff.
Yeah, yeah, it does. It does. You know, it's challenging just to get the, to even find a way to draw it is difficult. You know, it sounds simple, but it's not simple once you start trying to do it. You know.
Okay, so this particular diagram, the blue arrows have little dots inside which represent the hat. And some of them, the hats are missing because they're not polarized the right way.
Right, right. But you sort of have them in mass. You have them in different densities. I mean, they're very nice drawings, though. I do like the art of them. So it's kind of molecular almost, or cellular. You know, it almost looks cellular,
Ah,
like a disease.
right.
You know?
Well, so one of the things I came across last night was I looked into cell biology a couple of years ago. It just was interested in it. And this does remind me of basically flagellum entering a cell. And when you, and anyway, I'll just continue through these diagrams. I had another thought. I don't want to distort your theory, but I started to think differently. Might be interacting.
Yeah, you're entitled. You leave it up for a minute. Talk while you show the image, just so it stays on. Well, here I'll click on your. If I click on your icon, it'll stay on.
Yeah.
In that way, I'll still see this stuff there.
Don't forget to flip it back to yourself. So
yeah,
basically, this is a dipole, right? Obviously, you know what that is. One's not positive and negative, and as it comes across, somehow it interacts with the dipole there, but I can't work it out mentally as to. So it's actually rotating the bit, but maybe it's a little bit.
Yeah, well, at first I had a lot of rotation in my models, but the more I thought about it, I said that's just a convention I'm kind of stealing from the big universe. And, I'm thinking the small universe doesn't need to do all that stuff. In a sense, it almost can't do it. Because that complexity that's more complexity than this hat model can provide. It can do something that might in the end approximate a circle, but it's really not going to be anything close to a circle. It's going to be so elise and so jagged that you'd never call it a circle if you saw it drawn. You know what I mean? It would be so eccentric in the sense that everything would be going all over the place. And in the end, it's going to end up in 60 minutes right back where it started. But the fact is, it's not going to get back where it started in any kind of circular it's only going to be circular in the fact that by Maxwell's equations, it'll come out neutral. But you know what I'm saying? It's only coming out neutral just because of those kind of equations just really deal with conservation. Like there's no extra gravity if you walk sideways. You know what I'm saying? You're not doing more work against gravity when you walk sideways. You're only doing work against gravity when you walk up. And you're only gaining when you go down. So all the sideways motion is exactly neutralized in all of Maxwell's equations. That's essentially what they do. Is just it neutralizes all the irrelevant movement. So you can have very eccentric movement, but in a sense, it's not eccentric because all you're really counting is the up and down part. You know what I mean? You're only counting the part that's relevant to the force.
Probably getting a bit too complex for me. Hound, first things first, make sure you take control of the camera so it's back on you again.
Are you done picturing?
I've got one last picture. So
okay.
See this is a magnet.
North
Pole versus North Pole versus South Pole. And I've got a request. If you could please duplicate this and show me what's happening with the quanta. So these are quanta in the center.
Yeah, well, they wouldn't be dipoles, so
Correct.
quanta, so you can't call them quanta. Oh, you faded. A little bit of lag here, maybe. Hopefully, just lag. Hopefully. Hopefully. Could be me even, so, my connection might be dicey or insufficient to the purpose or something. Could be, unfortunately. Let's see, where are we? How come the speaker's still on there? I don't need that window open. Come on, YouTube, save us, please. Do not force me to be angry with you. Uh, 1020, that ain't the right room either. Where's the room anyway? Open a room link. Where the fuck is it? Oh, this is going to be irritating, I'm afraid. I don't know who's dead. Alright, live streaming. Wow, it is 5 days. That's a long time. Events. Let's see. I don't know what happened to my events. What happened here? Let's see if it's still working. It looks like it still is. Alright. Is it still working? That's me, yes. So it's just he's the one that's dead. Still is. Okay. He'll just have to try again. That's what he'll have to do. See if there's anybody in the what's all this stuff? Angela. Oh. No, stop it. Not do this. Whatever this is. Too many thingies. Anyway, so where was I? All right, so I'll go back to what I was saying. So he was just showing guys, so magnets. But yeah, the magnet thing is quite interesting. So I was doing more contemplating on the fact that you can have and this is, it's much simpler than I was thinking it was. But the fact is, see, this is a magnet. Yes, and these little things it's another magnet, just a stack of magnets. And you can sort of might be able to tell that I'm just flipping it over and then flipping it over. So it's the wrong side is sticking to the magnet. And that's the interesting part, right? I mean, they're supposed to have rules about that. The north side isn't supposed to stick to the north side, and the south side isn't supposed to stick to the south side, but it is, clearly. It's sticking, it's working. And it's because this is, when you have a size differential, this magnet becomes effectively a monopole in this region, because there's absolutely no way for any of the south pole effect to get anywhere near this magnet. It just can't affect it. It's just impossible. So it can't do the repulsive thing effectively, when it gets close. As soon as it gets out to here, it does seem to, you can feel a little bit of the tension right here. There's a little place where you feel a little bit right there, but out here you don't feel anything. And right here you feel a little push away, and then once you get past that line, it's essentially a monopole, and that is kind of interesting. Because it's against intuition, magnetic intuition, if there's such a thing. And but yeah, so what's really happening though is, I guess the magnets are just, because there's no opposite pole for it to be repelled by, it's still just attracting to the attractive forces still exist on the other magnet, so they're still doing the push in thing at that point. They're just doing it upside down because the other side of the magnet is neutralized. It has no effect because it's basically none of the south pole energy can get to this middle point. Now, it's a little different when you get out here, I think. Let's see. Yeah, it still works out here. Both sides will still stick. So, but it is curious. I wonder if it works out here. Yeah, it works even out here. All right, so that I'll have to change the theory now. Yeah, because it really shouldn't work out here. Okay, so that theory goes, but it's curious that the polarization appears to kind of change, because both sides stick fairly well. I mean, and technically that shouldn't happen. Yeah, they're supposed to be repelling each other. Anyway, so curious. So it probably just has to do with the size differential between the magnets, and the one magnet is just totally overwhelming the domains on the other magnet and obliging them to switch or something like that. But we'll see. Let's see. Shut up. Fighting with people already. Futa. I don't know what Futa is. Anyway. Gender is a lie is kind of a weird name. Yeah, anyway. Really obviously stupid name. Yeah. Yeah, stupid. So, where am I? Oh, I'm tired. That's where I am. So apparently Australia was nuked by Iran or something. So, yeah, out of luck. It's a social construct. Well, I'm just saying it's just kind of silly. I don't know what I don't know. How can you? It's just a stupid thing to say. It's just like saying eyeballs are a lie or something. It just, I mean, quite obviously the difference between ovaries and testicles is pretty substantial. Sperm and egg, I mean, they're really not the same thing. Well, masculinity and femininity doesn't really have anything to do with gender. So that's where you're making your mistake, I suppose. Well, I don't see how my physics theory is at all subjective, but whatever. Objectively, there's reasoned arguments. I mean, the reasoned argument made about regarding the difference between push force and pull force is a reasoned argument. It's not a subjective theory. But anyway, Michael is back. Australia was not bombed by Iran, so my false news report should not be taken seriously. Australia apparently was not nuked by the Iranians. So,
the way things are going, you'd probably be friggin' the US will be bombing us soon.
Yeah, well, yeah, who knows?
The Asia pivot. Have you heard that?
Doesn't sound good, but I suppose it's a girl doing it. It's probably okay.
Did you see the Philippines has changed its allegiance to China?
Yeah, well, it makes sense. I mean, America has been very, very bad to the Philippines. So you have every reason to say, "Fuck you." Yeah.
Well, I didn't see the Philippines' economy has improved much over the last 20 years. If anything, it's become worse.
Yeah, I'm just saying we haven't done them any good, so I can see why they're turning someplace else.
Anyway, this is not the geopolitics draft science discussion, is it?
It doesn't intend to be, but it accidentally backs into it now and then.
Yeah. Okay, so we got cut off before, and I just I did have one request, so I'm just going to flip up the picture of the north and south poles of the magnets. Pretty simple diagram. Just wondering if you could perhaps, in some spare time, draw something similar and show me how the quanta interact between a north and a north and a north and a south.
Yeah, I could probably do that. So, but what are
Yep.
those things in the middle between the two magnets? Those are just little
Yeah.
magnets, like iron filings or something?
No, they were supposed to be quanta, and it is incorrect, and you picked it up. They were dipoles, because when I started thinking, it was like, I wonder if quanta, when we talk about the polarity of quanta, it's like, well, this has got to be simpler than a. This has
Yeah,
got to be the.
they really can't have a polarity because that would mean, a dipolarity. They could have a monopolarity, but they can't have a dipolarity because that would break the whole speed of light constant thing. And just they can't be force relevant.
Okay.
They are force.
Oh, yeah. Okay. So if you get some time, if you could just draw one, and then we can discuss it the next chat. But okay, so I've got a list of statements. You can take them as questions or statements, and just so. I do have a question about the speed of quanta. So, okay, why are quanta moving?
It's like saying, why is there a universe? Yeah, it's just the way it is. Whether it
Yep.
blew up or whether I had lots of ways to explain. Like the universe has a error. It fractures, and what is it? It fractures into these little bits, and they're
They just are.
their nature is to be like spring loaded in a sense or something, or whatever you want to call it. It's like they're instantly, it's like the definition of antimatter and matter or something, or space and anti-space, or they're just kind of anti. And the consequence of anti is you just go, and you're against everything, and you're going as fast as you can away from everything. I don't know how to say it, but obviously force doesn't get bent by anything, so it doesn't have any preference except to go as fast as it can in the one direction. But no, I don't have it. Put it in another way, I don't have an answer to that question.
No problem.
God did it.
Yeah, that's what bothers me, is that it is like that, isn't it? God did it.
Well,
Anyway,
every description of reality is going to always be stuck. There's always going to be a place where you can't go. The evidence trail is going to end. No more footprints. No more, and you're just going to be stuck with saying this is as far back as I can go.
Yep. You're familiar with bottle glass?
I'm familiar with bottles made of glass. Yeah.
Yep. So the bottom of a bottle is a round, and in my home I've got bottle glass, and the bottle glass, they're all. I was looking at it the other day, and I just thought possibly these quanta are stationary, but I don't want to distort your theory, but I'm allowed to think.
Yeah, I don't, like I said, I don't have any necessity to make any variety of quanta. So I don't have to, in my opinion, the moving model covers everything. If I make any part of it stationary, then I'm going to have to explain how the stationary bits move. You know what I'm saying? So unless the stationary bits are always stationary, that is, that there's some place in space where they could never move from, then I'd still have to explain how I gave them velocity, because the other piece would lose velocity. You know what I'm saying? The momentum argument would come into play, and you'd be stuck with the idea that how can I make one thing move without making another thing stop? That's the conservation argument. So something else would have to stop. For me to make something that was stationary move, I'd have to make something else stationary to have conservation. So I'm just saying, it sort of, I don't think it would work.
Yeah, and that's something that we're not even talking about, so that's fair enough. Okay.
It's an interesting question. I hadn't given it any thought, but yeah.
That's all right. Well, I often review multiple times your videos, and I come across the very first one that I made with you, and one of my first statements is quite clearly a lie. And I said, I can't ask you anything intelligent, but that was obviously bullshit. I hope you regard these questions as somewhere intelligent anyway, for an Australian.
Yeah, well, exactly. I do have to put it in context.
Yeah.
So you're doing miraculously well for an Australian.
I'm trying very hard. Okay,
Well, I
so
actually did watch. Is his name Carruthers? You have some Australian guy that comes here and does the circuit, trying to debunk Einstein and dark matter, and he's connected with the whole electric universe. And I have him on the other. Let me just switch computers real quick. I'll just take a look.
I've had a look into that electric universe, and I know you're not sort of obviously aligned with them, but I did. That's where I started with sort of my alternative science. Like they do have some interesting things to say.
Yeah, but they're just so full of shit. So yeah, the guy's name is Stephen Carruthers. So
there's two of them in particular. That name doesn't ring a bell, but there's another guy. He's a grey-haired fellow with a beard.
This guy was just Australian, very Australian. So anyway, and I'd seen him before, but yeah, it's just that I don't. He's kind of irritating. Well, obviously everybody's irritating to some extent.
Most of us are.
Getting into some of the complex field equations, talking about tensors. This is all the calculus and stuff. And he's like pretends like he's not doing that, but that's all he does. But it was all kind of gimmicky, right? Because there's a whole part where he's talking about how, well, black holes can't exist because this equation, blah blah blah, and the equation, basically the equation was saying was, you can't use this equation if there's other material bodies in the map. You know what I'm saying? Because that's the gravitational effects quite obviously would change the results of the equation. Right, so it's just it's a one body thing. So it has to be a one body equation. And so he was basically arguing, well, you can't have gravity if there's only one body, and blah blah blah. And it's like, well, quite obviously, yes, you can. You can calculate something's gravity as a calculation, and yes, you can test for it by putting a charge or a mass in the environment. But if you wanted to find out, like, say, the sun's gravity without planets involved, that's the equation you can do simply. If you want to find the sun's gravity with all the planets included, well, that's a very complex hunk of calculus. So that's the argument that was being made. This is a very complex. The point was being made is, he was just cheating. He's basically saying that they're not allowed to somehow exclude all the mass in the universe. And of course they're allowed to, because it's necessary. You can't include all the mass in the universe, but you'll break the equation. You know what I mean? You might know what I mean. Well, I just mean that the argument was very complicated, and he was taking a very simple cheat and basically saying, I gotcha, and the I gotcha is just complete bullshit, because there was no other way you could have a field equation if you didn't exclude all the mass in the universe. You have to exclude all the mass in the universe, or you can't do the equation.
Is it something similar to, are they providing people with an alternative to general science, general physics, but it's just more bullshit?
Well, I'm just saying it's that electric universe people, so they don't really have, their counter theory is kind of mumbo jumbo. I can't make much sense out of it, but everything's kind of electric, and it's electricity that does everything, and gravity's electricity, and it's all this magnetic. It's kind of like the Ken guy, you know what I mean? It's all kind of
hyperbolic.
Yeah. There's no, it's this ether thing in this vague way that they don't explain. So yeah, I can't. I wish they had something more concise, but yeah, it's not even concise enough for me to be able to argue it, because it's not even. I mean, I can't. I can't prove there's no leprechauns, and their theory is pretty leprechaun-y.
Yeah, are they? So it's sort of like word salad.
Yeah, well, exactly. It's just words that you're like, okay, it's electric. Well, what does that mean? Well, there's a charge. There's electric charge. Well, what does that mean? You know what I'm saying? Somebody can say that something moves towards something because of an electric charge, but right, that's not really telling you how it moved at all, right? That's not telling you how or why it actually moves. So to say it's like the bent space argument. You know what I mean? It's like, Well, how does bent space tell mass how to move? You know what I mean? That's not a mechanism. It's not a real description, I guess is all I'm saying. It's a cheat.
Yeah. All right. Listen, I've got a lot of questions here. I want a lot of statements anyway. So, if quanta move at the speed of light, when electrons travel along a wire, are they filtering quanta and ejecting them back out and refocusing their alignment?
Well, they're obviously not moving as fast as the stream. So if we could concede that in a way. So if we said there was a stream of quanta, I could argue that some percentage of that quanta is going into the electron and accelerating the electrons. But the electrons are sort of like boats. You know what I mean? The water's going faster than the boat can ever go. So even though the boat's in the stream, it's not really going to go as fast as the water. The water's always going to be going faster than the boat. Good
So,
enough?
no, not really. So it is a good starting point, but what I'm getting at is the electric field surrounding a wire when an electron passes down it. I'm asking you if when the quanta hit the electron, how are they creating an electric field? So are the quanta being
acceleration? So you have to think of the electron as being stationary. So it only happens while they're accelerating. So it's not velocity, it's only acceleration that makes an electron expel the EMF. So we're talking about the stuff coming out of perpendicular. So perpendicular to the acceleration, so the stream is moving this way. So we have a bunch of quanta going this way. We have an electron sitting in it, and it's getting hit, and it's gaining acceleration. When it gains that acceleration, it expels the blues going the wrong way. So the blues in the other two perpendicular dimensions, right? So you understand there's three dimensions, this way, and this way. So this way is being used up by the acceleration, obviously. And so this way and this way are going to be the perpendicular dimensions that the electron will get rid of the extra blue now, because now it's absorbing blue from the stream. So it's eating stream blue, and it's getting rid of blue going in the perpendicular dimensions. And so that's what's creating the EMF.
I'm trying to just visualize. So when an electron travels down a wire, are the quanta at a large distance being affected? So if an electron flows down a wire here right now with me today, are quanta somewhere out in the end of the universe being affected?
No.
Almost instantly? They're not?
Nothing can be affected instantly. Everything has to travel the speed of light. There's nothing.
Almost instantly.
I'm just saying there's no instant. There's speed of light. Speed of light is pretty slow on universal scale. So I don't know what you're saying exactly.
Yeah, no, that's a good point. No, you picked me up on the correct. So
you think of it as light. So if you turn the field energy in the wire into, say, photons, and think about it that way, like they're actual photons traveling through the wire, so that and that's the field energy that the electrons are being influenced by. And then think of the energy coming off the electrons, perpendicular to that stream flow, right? So the stream, the boat is ejecting missiles or whatever, okay? And that's those quanta. If you thought of them as light, that's how they're coming off of it. They're being irradiated off of the stream flow perpendicular because of the existence of the electrons in the stream.
Yeah, I think that's why at the beginning of the question, I'm trying to ascertain if the electrons themselves are filtering incoming electrons and deflecting them at an angle. It's a bit hard to...
No, they're not. Electrons are kind of irrelevant to conductors in the sense that it's only the electrons in the conductor that are relevant, so the ones around it.
Yeah,
so you have to think of them as being, they're producing the field energy is bouncing off of them constantly between them, so they're repulsive. So they have a bunch of this field energy that's going between them all the time. So they're, like I said, you have to think that you can never change the density of the field energy. You can only change this thing we keep calling polarization. And the point is that you have this polarization that's hostile to the electrons, not hostile, that makes the electrons dislike each other even more, okay, is what the field energy is made of. And it's going to accelerate the electrons because it's the stuff they're made of. All right, let me think.
Yeah, so you're talking about basically it's magnetism between the electrons and a creation of shadowing on one side, right? So
right. And you're injecting into the stream is only one color, okay? It's only one kind of polarization. So it affects only the electrons. If I can, that's not the best way to say it.
No, I understand how difficult it is because I understand it's tough. Let's just move along.
Well, here's an example of just real quick. Okay, so here's a conductor, and say if I have a transformer, right? And so I'm going to put electricity into the wire that's going to cause this effect. You know what I mean? I'm going to affect it magnetically with a field that turns on and off. Well, what's really happening is the electrons are getting pushed both ways. You know what I mean? They're just being evacuated out of the wire. So that's really the polarization part. It's just the fact that you're creating a neutral in the middle and you're polarizing the two ends in a sense. Well, let me see if there's a better way to say that.
Well, the electrons have to travel one way.
Well, I mean, the polarization is obviously going to be different in the sense that you're going to end up with one side of the conductor. At one point, it's going to be a lot of electrons, and then the other side will be a lot of electrons. So they're obviously moving conducive to that pattern. But I'm trying to think of the better way to say that. But it's just the real point is it's the on-off part that makes it possible to create the idea of current. So what you're really doing is just pushing and then letting them back in, then pushing them out, then letting them back in, then pushing them out, then letting them back in, pushing them out.
Yeah, that's alternating current there, right?
Well, yeah, well, that's the only way you can. That's the only way you can maintain a current in a wire. So if I take a regular magnet and put it next to a wire, I only get a current for a split second. Only when I initiate the first contact. But if I leave the magnet there, it just stays no current because I have to keep moving the electrons to force them to create the movement of their field energy. You know what I mean? I have to keep accelerating and deaccelerating them for them to absorb and emit the perpendicular field polarization.
Yeah, so I had in my mind that you'd applied a charge to it as DC, but you're talking about putting a magnetic field around the wire, and you can. Yeah,
if you use DC, then you actually have to move the magnet. Something has to move. But if you use AC, then you don't have to move anything because the field is reversing. So that's the movement. But anyway, I don't want to get too specific on that. I thought I would clarify, and I don't know if I did or not. So
no, that's all right. I know it's difficult. I guess I hope that's why you understand it's hard to. For people watching this, when they obviously hear you talking about fish and quanta, I know you're trying hard to make it really simple. But even that, I mean, they're analogies, right, of what we're trying to even work out and talk to each other about here now.
I don't think they're analogies, though, in some ways, just because there's a good visual way of understanding just the momentum arguments. That the fact is the school doesn't move unless the fish move. If the school doesn't move the fish move the school. So it does help visualize some of the mechanics that are accurate.
Yeah, no, it is. But when you first come into your videos and you hear you talking about fish losing their skin, it's like, what the hell is this guy talking about? But I mean, I've looked at a lot of your videos over the last 6-7 weeks, and somebody probably, I'm not the sharpest in the toolbox, but I haven't done physics and this stuff for a long time. But I'm getting there, and
Well,
somehow the other day.
it just fits with an understanding is all I'm saying, is that the mechanics of things you see in the real world become a little more visually understandable when you kind of recognize that, I get it now. The gravity's got a whole bunch of this stuff coming down. And to be able to go into space, you have to compensate for all that stuff coming down, so you have to create all this extra stuff pushing up, and
Well, I'm going to jump ahead to a.
Yep.
I've got lots of statements, but one of the things I did have in there was, let me just look for it here in my list of statements. It's to do with gravity. Well, hang on. Here it is. So matter is a mixture of protons and electrons. Protons can only be comprised of quanta of a polarization type A. Electrons can only be comprised of quanta of a polarization type B. When these two quanta types are mixed, they form matter and are subjected to random incoming quanta of varying polarization, which is gravity. Gravity is a byproduct of the randomized quantum movement. Is that all correct?
There was just a catch in there where you said matter is made of the two. Well, matter is only made of the two in the indirect way that all the A is in electrons and all the B is in protons, and then the neutrons have a mixture of the two. But that it is segregated in the matter, so you can't really say matter is a mixture of the two and be entirely accurate, because it really means that protons and electrons segregate those two polarizations.
But in my defense of those statements, if I just looked at a block of lead, it would be a mixture of protons and electrons. Yep.
It would be a mixture of A and B, right?
Yeah. So when I think of matter, I think of stuff like cars, horses, chocolate, but you can look at matter as like an electrons, and a proton is a piece of matter. Would you agree?
Well, I think it has to be, in the sense that obviously has the three-dimensional mass kind of thing. So I guess that's what I would call matter, is anything that has, well, it could have two-dimensional mass. So let's not be presumptive and say automatically that electrons are functioning in 3 dimensions, because they might only be two-dimensional objects. So they might be like a galaxy. Okay, they might contain a lot of stuff, but it's on a flat plane. So they might be only existing in 2 dimensions like galaxies, not 3 dimensions like a sun.
Yeah. I actually steered away from your initial statement earlier. We were talking about gravity, and I was looking for the statement on gravity that I had in here somewhere, but basically, if you throw a ball up into the air, that's got inertia that you've given it, but once that inertia runs out, it's going to be subjected to the field of gravity, which is quanta, which is always present. Everything is so.
But it doesn't run out. Its inertia doesn't run out. Its inertia is forced out of it. So let's understand that from the minute you throw it in the air, it's being constantly converted by gravity. It's losing its inertia. It's losing its velocity and its acceleration constantly. From the moment you release it, its velocity is being converted by the force of gravity. So it's re-accelerating in the opposite direction.
Is this fair to say that gravity is probably the weakest force, but it's forever present?
Well, I just don't bother with this weak thing, just because it's very strong in terms of your position. So if you're an electron, gravity is very strong. If you're a proton, gravity is very strong. Now the field, once you put the other crap in your field, then gravity gets weaker because it's getting blocked by the crap surrounding you, if you get what I'm saying. So but in its raw form, it's a very strong force, because it's exactly the thing that's actually keeping the electron together. I mean, gravity is the relationship between the proton and the electron is more about gravity converted into magnetism, polarization. But the thing that's actually holding the electron together is pure gravity.
Yeah, I don't want to use, I know I used the word weak, and I'm not borrowing that term weak gravity force from other science or physics statements. Why I'm saying that is because you or I can overcome the force of gravity just by blowing a piece of paper with our breath, right? So, but I think we're on the same page when. So I'm saying that gravity is very weak, but because it's forever present, ever present in the universe, it'll always overcome any other force.
I
Eventually.
guess I'm just saying that I think it's a very strong, it's the strongest force. It's the only force, technically. Okay, I mean, technically, it's the only force there is. The other two forces are just a perversion of gravity. Light is riding on gravity. It's just that it's, put different hats on the
Yeah.
gravitons, and magnetism's doing the same thing. It's just riding on the energy that was gravity, that is gravity. So, in that sense, that obviously, when you filter, you can make something more potent, right? Doing, like I said, the bar thing, the jail cell thing, right? You make this more potent if the bars are going this way. You make this more potent if the bars are going this way. So I'm just saying, obviously, you can change potency, but the real force is gravity. So I'm not saying you can use your words. I'm just saying that to me, it's not a weak force when you look at a galaxy spinning through space and you say the only thing holding that thing together is galaxy. It's gravity. It's pretty fucking strong force because that's a hell of a lot of shit to be moving.
Yeah, and look, it's not really relevant to the conversation anyway because I think it's just demonstrating that I'm trying to think about what we're discussing. But really, all that really matters here is how the quanta are interacting with protons, electrons, and neutrons. Yeah.
Well, that's the substance of the mechanism is, I mean, nothing really reacts with an atom, just like nothing really reacts with a school of fish. It reacts with the individual fish in the school. You know what I'm saying? So there's some physical part of the tank that hits you. The tank doesn't run you over. The tread runs you over. The front of the tank hits you. The gun post hits you. You know what I'm saying? Some physical thing hits you, okay? Not the tank. Right? I could just say there's only a tiny piece of the tank that actually kills you.
Yeah. Okay.
All right. It's like the whole bullet doesn't kill you. It's just that shit at the end does all the work, right? I mean, it does all the.
Yeah.
Those are the nasty bits, So it's like, yeah, okay,
It's just
you file off those nasty bits, it'll be just fine.
it's just those quanta at the tip of the spear.
Yeah, obviously, But,
All
but
right. Listen.
it's sort of true. I'm just saying that that's the truth of it, is that you have to always reduce it to the function of the actual mechanism, because it is not the actual spear that is doing the work. It actually is just the ones on the very end.
Yeah. All right. Okay. I do have to ask. I know I've drawn a lot of diagrams, but I need to ask you about hat wearing and fish. So, so I understand that we can have the analogy of when the fish hit the fish school, their skeleton. They exchanged they exchanged their fish suit, and the skeleton of the fish leaves out the other side. You know what I'm talking about, anyway.
Well, I know you're taking it now. You're taking it to the reverse arguments. It's
Yeah.
Okay. We got naked fish, and then we got fish wearing pants, and then now you're making it, naked fish versus de-skinned fish.
Yeah. No, I want to be real careful because okay, so I do have to ask about polarization and hat wearing. And I know you've been over it many times, but I need to make sure that I clearly understand this. Is hat wearing just a term for polarization?
Yeah, I'm just using it as a way of identifying polarization. So like I
Okay.
said, I don't mind using red and blue. I don't mind using
Gotcha.
colors, hats, clothes. I'm just trying to say there's an identifiable segregation. We can identify one thing from another thing. They are distinct, and then you can understand how the clumping can happen. Because when
Okay.
something is in a clump, why does it stay in a clump? And I can explain why it stays once you understand how it's different.
Yeah, all right, let me just keep going on because I have to get to I'm getting to shadowing. So I'm just going to run through the rest of these statements. And I know you've just answered that, but are you suggesting polarized quanta are being repolarized from type A to type B when they interact with quanta in the electron?
Yeah, well, originally I thought there had to be some transitions, but I'm actually thinking now that nothing exchanges, so it's only reflections. So you either take the suit or you bounce off with your own suit.
Yeah.
Okay, so you
Okay.
keep your clothes and you go in and you either change your momentum, so you're a certain color and you switch direction, or
Yep.
you go the same direction but you wear a new suit.
Okay. So I'm going to show you a diagram here on the screen. So you might want to just put the camera on this.
Yeah, I'll do that.
So here we have blue quanta, and they've got, these ones have all got little dots. So they're hat wearing. They enter the electron. They dump off their hats, and as they exit, it's lost its hats, which means it's lost its polarity. So came in, interacted with the electron, dumped off its hats, and it exits, right? This now creates a shadow.
Is that correct?
Well, it means that the field energy has now been changed by that event. So something on the other side of that, right? So something forward, linearly from that position. Yes, that's the shadow effect in the sense that you've changed the polarization. You didn't change. Yes, well, you're always just changing polarization. I mean, I say that you can exchange momentum. You're not really exchanging momentum. You're just exchanging polarization. But again, I don't. Yeah. It's just really, because as I've said, the arrows never stop. So you're never changing an actual arrow. An arrow is always going to be coming at you. The question is, when it comes at you, what did it go through? And what is the polarization that it's carrying? So that's all that really matters, is you're going to get hit with the same number of arrows all the time. And the only thing that can change if I'm standing next to you is that I'm going to be changing the blue and the red. You'll have the same amount of blue and red because I'm not gravitationally significant. You know what I'm saying? But I'm going to definitely change where you're going to get hit with blue and where you're going to get hit with red. The amount of blue and red will be the same, but I'm going to filter what's going to hit you just by existing.
Yeah, so this is where, and I understand it is difficult, and I know this is probably a work in progress, but I wouldn't be wasting my time if I didn't think you're onto something. And not that I'm anybody important, but I think what this is, I think this is a very good explanation for gravity. But what I'm concerned about is, so when I start to think about this, right, if some of the quanta coming down on top of me are gravity and they're pushing me down towards the surface of the Earth, those quanta weren't blocked by anything, right?
Well, again, they were blocked in the sense that it required you to accelerate in a sense, okay, in the sense that what you will possess will change in terms of what dimension defines you. Okay, so the stuff that is polarized will exchange in the sense that the arrows going through, you've got lots of gravitons going right straight through you. So your substance is still made of a lot of stuff that isn't blue or red. But the point is when you accelerate, you will be expelling your blue and red, okay, perpendicularly, because you're going to accelerate. So what defines you in terms of how much mass, how many little arrows are pointing in what direction, will no longer be balanced. It's going to be more of it's going to be pointing that way. More blue and red will be pointed in the direction of the center of the Earth.
Yeah. But, yeah, okay. So What? Okay, so as a thought experiment, right? If I put above my head a 10-foot thick piece of lead, why is that not blocking
It is.
quanta?
Well, it is, but it's obviously blocking both A and B. You know, both electron and proton. So it's converting the blue is converting to reds, and the reds are converting to blues, and so you end up with the same end product. Okay, in a sense, it's not filtered, so it's not magnetism. So, and the gravitational effect, as I keep trying to imply, gravity is a nuclear force. So the only way gravity really works is by creating the plane argument, right? The reason why gravity gets weaker as you go further out is because the Earth is curved, right? So if you could if you could flatten the Earth out, then it's like the light argument. You know what I mean? If I made an infinite plane, the light would be as bright here as it would be here, as it would be. I couldn't go. It doesn't matter how far away I went. The light would be just as intense if I made this plane of light big enough. You know what I mean? So if the energy is spread out, there's no way to dilute it. So it only dilutes by being curved. So curving is what dilutes light. That's what creates the problem of divergence. You know, where the light separates and becomes weaker and weaker as you go further out.
So you're talking about a focal point, right?
It's sort of, but I'm talking about it's a density argument more than a focal point, because the argument sort of is you can sort of understand if I had two things. If I have one light bulb, and it spreads out like a peacock, right? The rays.
Yep.
Right? And so you see how it gets weaker and weaker as you go further out, because fewer and fewer rays can hit you, right?
Yep.
So if I start making a lot of light bulbs, then for whatever one diverges from you here, this one's going to converge right into you. So all of the divergence gets lost, because now for every separation that happens over here, the other light bulb is going to hit that spot. You know what I mean? So for every way it's spreading, it's going to keep getting hit by the other stuff on the sides that are pointing right at it. So for every bit that's going this way, there's a bit on the side going this way, if you can get me.
Yeah,
so
no,
it ends up being the same density of force. Okay. All right. So, but to get back to your real argument, you know, why you're basically just saying, why isn't the gravity stronger, right?
No.
Well, you're saying, why isn't it strong enough to make you anti-gravity?
Yes.
Right? You're saying I'm putting a big giant thing here. Why isn't blocking all of that force causing me to kind of move up into that thing? Well, that's the whole point. Is the thickness of the Earth is 4,000 miles, right? The diameter, something like that.
Probably.
Okay. Well, so you got to think that the 8 meters per second requires 4,000 miles of material. That's how thick the filter had to be, right? To just give you the 8 meters per second. So obviously 10 feet of lead above you, by comparison to 4,000 miles, 10 feet to 4,000 miles. So you have to think that's how diluted the effect of the lead's going to be.
I'm satisfied with that answer.
So it's there. It's just that it's so diluted because it's just not, there's not enough filter.
Yep. So very good. Very, very good. Had you come across that problem in your own mind previously, or have you just come up with that answer out of your ass right now?
Yeah, no, I've already had to think about it. It came up right away, just because the whole idea of gravity just fucks with your head all the time, right? You're saying, how is the Earth stuck in the sun's gravity, right? Because this is a fact, right? The effect of gravity where the Earth is to the sun is 0.0014, something like that, meters per second. That's how weak the gravity is where the Earth is from the sun. So if I was just standing where the Earth is in orbit in the universe, right, the sun's pull on me would be 0.0014 meters per second. I mean, I would move towards the sun so fucking slowly. You know, it'd take quite a while for me to actually move enough distance to really start gaining some acceleration. So that's how weak the sun is. And you're saying, how is the Earth getting stuck in that? I mean, why doesn't it just plow right through that? That's nothing, that gravity. How the hell is that holding the Earth here? You know, but again, it's this density argument. You have to think about it in terms of all the little bits are the thing getting pulled. And so when you combine all of their effects, then you're saying, like, for the little bit moving the speed the Earth is, that amount of gravity is a lot of gravity for a little bit. You know what I mean? So if I make the thing small enough, then it was more visually understandable how a small amount of gravity could keep it in an orbit. You know what I mean? Because the big thing didn't make any sense. But that's an intuitive problem. Well, anyway, yeah, I don't think I illustrate that very well. But the point is there's lots of stuff that where it doesn't look like it makes sense until you start thinking about it.
Yeah. I will do what I usually do, and that is I'm going to rewind the tape and watch that part.
Yeah. Well, I'm just saying, I'm sure it wasn't very used. I was just trying to explain how my own difficulty with the whole mass argument was one that I had to think through, and that's where I got to the idea of it's even understanding that if you're going to the center of the Earth, theoretically there's no gravity. It's zero gravity in the center of the Earth. There's no, it wouldn't fall in any direction.
At least we've both see, you've had 3 or 4 years to think about this, and I've had like 6 or 7 weeks. So at least at least, you know, I'm trying to think along the same problem lines that you've encountered probably.
Well, I understand, but it shouldn't take you near as long, because I should have done all the filtering, and so it should be a lot more clear. You know, I should have cleaned it up a lot better than.
Well, it's taken you 4 years, and it's only taken me 6 or 7 weeks. So I guess that's a testament to what you have been.
I'm just saying, I'd say that still. That's I wouldn't give myself a passing grade if it takes 8 weeks to explain. I'm not doing very well.
But the thing is, no. The problem we've got, right, is so when I work here, I listen to your videos, and I have to work, but I can take in your information, but you're not there to ask questions of. I mean, if it was a classroom environment, you'd probably understand this in an afternoon. But the thing is, it does raise a lot of questions, and I have to wait days before I can speak to the professor.
I'm just saying that I've obviously not done a very brilliant job of like I said, it's been a work in progress, and so the fact that I have occasionally had to change you know, the fact.
That's why I said just before, it is a work in progress.
I mean, I was very clever to call the channel Draft Science, because I should, you know, because it is drafty.
Yeah, and look, I'm not picking on you, but I am letting you know, I was looking at it, I have actually got it listed at the top of the list here, one of your Draft Science videos from your crazy dating system reversed on the 23rd of September. We had different colors of polarization. It's like, oh man, when you're trying to understand this, when you go from blue to red, back to green to black. So sometimes, and I mean, it's 2 in the morning there, and so look, it's not all your fault, but anyway, look, we'll just move along. So just scan through these. So the other day, it started to sink in what you're telling me. So I came up with some analogies of my own. So basically, with regard to quanta and filtering, if Professor Clouseau ran into the billiard room and smacked the victim with a candlestick, the victim is not going to move over, and as the professor leaves the candlestick at the scene of the crime, right? So basically, when these quanta come in and drop off their hat, they leave without their polarity, right? They've changed polarity.
Yeah, well, that's the only thing. Is one or the other. You have to think of it being exchanged, but regardless of how you think about it, it's either one or the other. I mean, either they're exchanging momentum or they're exchanging polarization, but they're obviously exchanging one or the other. But you can't do both, because then really things get messy. So you have to think of it in one. You either think of it as them exchanging momentum, or you think of it as them exchanging polarization. But I guess I would say logically, you have to say polarization, because the momentum exchange doesn't happen in certain circumstances. You know what I'm saying? You wouldn't be able to.
When you say momentum, do you mean deflection of angle?
I mean that, yes, you're either, like I said, it's the X thing. You know what I'm saying? You're either thinking of these things always, there's two things come in, two things have to go out. So that conservation always exists. So that's all I'm trying to say, is that you can either think of it as the two things going out as switching, the two partners have switched places, or they switched momentum. But that's all you got. They either switched the direction they were going, or they switched the suit they were wearing.
Yeah, so when the quanta comes into the electron and switches polarity, and it now leaves, so it comes in as type A and leaves as type B, right? Because it's lost its suit. So
well, let's just say that the stuff on the inside can't really leave, all right, until something else comes in. So think of it more like the stuff on the inside is a circle. The stuff on the inside just keeps bouncing back and forth. So it's reflecting off something else hitting it. So the stuff comes down, hits it, reflects back up. The stuff on the bottom hits and reflects back down. And the thing in between is just doing the exact reciprocal of that. You know what I mean? When that goes down, this goes up, and when that goes down. And so that's the pressure, that's how the pressure has to be even, right? So that's why I'm sort of arguing that if protons and electrons actually have equal charge, then they have to be equal density in a sense. I mean, I don't know how to get to that proof yet, but there has to be some reason, you know what I'm saying? That there has to be a reason why they think protons are much more massive. And I think the reason is that they're being fooled by some relationship with the neutron. But I don't want to get into that. Maybe
that's not true.
Well, that's all I'm saying, is they're being fooled by the measurement's correct, but the interpretation of what you measured is incorrect. You think you just measured the proton, but maybe you just measured the neutron and the proton, because you can never separate the two and still measure them. You know what I mean? You always need something to put on the scale, and you can't put the proton on the scale unless it's associated with some other piece of matter. You can't measure a proton in empty space, is sort of my point. You have to put it on a scale, and as soon as you put it on a scale, you've associated with a neutron, and you're really going to be measuring the weight of the neutron. It's funny, is I'm just giving a possible explanation for why they think protons are more massive.
Yeah, I'm having a bit of a problem, because I keep seeing that this quanta is coming into contact with an electron, and it's shedding its polarity, i.e. its suit changes. So the fish inside, the quanta inside the electron, absorb another quanta that comes in.
I shall draw a picture. Hopefully an understandable picture. That's what I shall do. I shall draw a picture and use appropriate color, and hopefully make this understood, and then it will be understood. Okay, so the electron, think of this as the electron. So it's just stuff going back and forth. So think of two arrowheads on all of this stuff. It just goes back and forth here, it goes back and forth this way, it goes back and forth this way. So it's just a bunch of quanta going back and forth. And what's making it go back and forth is this field energy is hitting it. So all of this field energy, the regular gravity, is reflecting. And it's only this blue, when a blue one comes in, that's when the game gets fucked, right? Because the blue one comes right here, and although it does reflect, it's still blue. So in a sense, it's just lengthening this line, if you get what I'm saying, right? So if this blue comes down, if a blue hits here and reflects, it's really just going to extend this blue line, right? You can sort of get that, right? Say if this is a blue and it comes down right here, when it hits here, this blue will go down, right? You get that?
Yep.
Okay, and the blue that just hit is going to go up, right? So a blue comes down here. I'll draw it.
Hang on. You take draw. I need to go and come back. I need to close this blind.
Yeah.
1 minute.
Oakley doke. I'll just improve the drawing while you're gone, and then you'll get what I'm saying. Maybe, possibly, hopefully. Yeah. Some chance of it, maybe, possibly, hopefully, that you'll get what I'm saying. Possibly, maybe, or not. All right, maybe I'll click on my window to keep the image visible. That will help. That's why it's closing blinds and such. It takes time. It's Australia. I have a lot of sun down there. Summer and such also. Lucky bastards.
Okay, I'm back.
Okay. So I have slightly enhanced the drawing. So you have to understand, this stuff's constantly moving back and forth. This stuff is constantly raining in. So let's understand, this stuff comes through and it just constantly keeps coming in. You know, it just keeps going right through.
So I need to clarify something, right? So I know this is wrong, but I'm thinking that this electron is a round ball and it has a membrane. Is that incorrect?
No. It only ends up being that in effect. That's what the school of fish is, right? The school of fish sort of looks like a round ball with a membrane in a sense, right? Think about a school of fish, right? Doesn't that what it looks like? But there's no real membrane, right? There's just the sides of the fish, or, you know.
Yes.
So this is the same problem. There's no real membrane. There's just the end result is that this might go a little bit further, right? Say if this blue arrow went further, it's sooner or later it's going to hit the green shit. You know what I mean? It's going to go back this way. It can never get too far out of this scale. It's always going to get. It's always going to be sent back. It's always going to be sent back. It's always going to be sent back. So that's what you have to just think about, is it's always going to be reversed, because it's sooner or later going to hit one. So let's say a blue comes in. The blue reflects this blue, so you got that part. This little bit goes back out blue, right? So that little bit going blue, you can see that's just like extending this line a little bit. And eventually this blue is going to get hit by a green, and it's going to be knocked back in. So it's going to just be part of the bounce again, right? So you sort of get that it, even though it went a little further, it's still going to go back into the system. So it's going to be part of the new electron is now going to have this blue, this extra blue in it. Right?
Okay, so
now you'll be getting rid of one of these blues going the wrong way, but this is the blue it's going to keep.
Still there? Okay, so my question is, let's just for the sake of, let's say the school can only get to a maximum of 100 quanta. Would that be fair to say?
Well, what I'm saying is that I think it's probably for electrons more like 1 million. But
yeah, I know, just out of that.
Yeah, but yes, so what I'm sort of arguing is that these electrons are basically telling you the field pressure, because whatever the absolute field pressure is sort of indicating to you how much stuff could actually be kept in this thing, right? If I put more stuff in here, then there'd be more blue going out that wouldn't hit green. You know what I mean? It wouldn't hit it soon enough. So it would get out too far. You know what I mean? Like if there was a lot of more blue in here, this little blue arrow might go all the way out here, right? And it might be this far away. Well, now this electron could be way the fuck over there by then. You know what I mean? It's left town while this blue was over here. So when this blue turns around, the electron's over here now. If you get what I'm saying, the electron will move out of the space, and now this blue is lost. And so that's how the electron is basically accelerating out of the other dimension. It's basically, when it moves, the stuff going this way and the stuff going this way, all of a sudden there's no electron anymore. If you get what I'm saying. I mean, the electron moves.
I understand you.
That dimension, it doesn't exist anymore.
Yeah, I do understand what you're saying, but I hadn't even contemplated that. So, I mean, you've just thrown another spanner in the works.
Yeah, I don't know if it's a spanner, but I'm just saying it's like I said, the black back and forth thing is what I came up with like maybe 2 weeks ago. You know, instead of trying to make it a bizarre circle, it's just easier just to say no, it just bounces back and forth. I mean, it's a straight line force. The thing is just keeps getting knocked back and forth, and that's all that's happening.
Yeah.
You know, it keeps hitting the external energy. The external energy says, no, you're not going this way. So it goes back the way it came. And this side of the side says, you're not going this way. And it just shoots it back the way it came.
Yeah. So an electron would be a compressed amount of quanta into a certain space.
Right. And it would be constantly in motion, in the sense that it would be constantly, you know, it'd be going a little extra this way, go a little extra that way, go a little extra this way, go a little extra. You know, it's never going to be something that would have a perfect edge to it. You know, it would always be, because of the field irregularities and how often it hits a green. You know what I mean? It's constantly jiggling. Its surface would be constantly moving, you know, in terms of its strength.
Yeah. See, I'm still I'm sorry, man, but I am confused. I know I understand what you've just said, but when something comes in and exchanges its fish suit, I'm just not getting that, because if it exchanges its suit, that means the skeleton.
It's not exchanging. I just pointed out to you. There's no. It's just exchanging momentum. If you really, you know what I'm saying? It's exchanging the suit, in the sense of what I'm saying is that when this green comes in, it doesn't really bounce off. Okay, theoretically, it goes this way, except it wears the blue suit. Okay, and the blue actually went out, and it's just wearing the green suit. So again, it's what you call a reflection. I'm just saying you can't get caught up in this. As you know, I just made this simple rule that a reflection, you know, there's no way to understand it in terms of when they're both the same polarization and when they're opposite polarization. And so I'm just trying to explain that you have to just think of it one way, as either the color changes. Whoops.
Mm-hmm.
Are either the color changes, or either the shit. Whoops.
Reflection.
Yeah, well, that's I'm trying to draw it correctly, and I'm you know, like I said, even, even drawing it, you know, it sometimes gets a little complicated because your arrow going wrong. Whoops, arrow went the wrong way there.
That's all right. That's all right.
So, but it's just this idea again that you can't see this. All right, this is impossible to see anything happening. Like, you can see it as a reflection, or you can see it as these things just going through each other, right? Kinetic, this green arrow went straight through and hit that green arrow. You know, you can see that as, like, say if it was transitioning from, you know, let me turn it this way. Yeah. All right, so think of two things coming in to hit each other, right? So you can think of it as this arrow went straight through and came out here. So this is the before and this is the after, all right? Yep. So you can see that you can think of it as being a reflection, or you can think of it as a going right straight through. And then when you do the polarized thing, though, it becomes quite obvious that the black seems to have reflected, you know, and the green seems to have reflected, right? But I mean, what theoretically could have happened is the green took on the black suit, and the black took on the green suit.
Ah!
So you can see it either way, but you can only allow it to be one way. All right, you can see it both ways, but it only actually did one of those things. It didn't do both of them. So you just pick one, and that'll be correct. But you have to pick one. You can't pick both. So either you follow the momentum, or you follow the suit. If you get what I'm saying.
I think I'm getting closer to understanding it. I mean, I wouldn't have drawn all these diagrams if something wasn't happening. It's just that
Well, I'm just saying, you can see it from this diagram. I'm just saying that I'm telling you that what really happens, okay, the truth is, okay, this green arrow turns black, okay, and this black arrow turns green. That's what happens in the real universe. Now, as a practical matter, it works if you just see it as a reflection, okay? But that's not what it was, okay? The black arrow actually did turn green. The green arrow actually did turn black. So if you go back to this diagram, that's what I'm telling you, is this green stuff that came in here and I'm saying is hitting this blue stuff. No, it really went right straight through the blue stuff and turned blue. And the blue stuff went right straight through the green stuff and turned green. Now it looks like a reflection, but I'm just saying that's what actually happened, is the little rays went right straight through, and all that changed was the suit they were wearing. So that's what I mean by the suit exchanging, is that the green comes in, hits the blue, changes direction, and wears the blue suit till it gets to here, and then it changed to green again, if you get me.
Yeah.
Okay, so it left the blue suit behind, okay, and it left with its green suit intact. So it only wore
that's the problem that I
while
had.
it was in here, and now it's free. It goes back to being green again.
Okay, that's the problem that I had, right? So you've just fixed it. So the black comes in, turns green, and then leaves black. But the problem I had was, if a black comes in and strikes a green, I was thinking, how the fuck is it leaving green? Because now it's been converted to something, and it's like, I know it's I know it's frustrating for you.
Right, the leaving part only happens because you fool the other dimension. You know, you basically move out of that dimension, so the stuff at the bottom level of the dimension is left behind. It doesn't, it's not, it went out when you moved up, and now it can't go back because you're left. So it can't hit you anymore.
Yeah, so I'm going to go and watch that again. I know it's frustrating for you, Gary, and I'm not deliberately trying to antagonize you, but the problem that you haven't.
It's there. I mean, yes, if you watch it again, you'll get what I'm saying. Is you just choose one. That's all I'm really saying is that it's visually more interesting to me to think of it as a reflection, because that makes it more understandable of the separation. But the actual truth is that it is an exchange. So I guess I should call it what it is, because it's an exchange. But I'm just saying that visually the reflecting idea just works better.
Yeah, I think you said something in this last immediate exchange that you haven't said in any of the videos, and I've watched a lot, and that is, maybe I missed it, but when it comes in and it's black and it hits green, I kept thinking, well, if this is changing its polarization, there's a deficit here, but you've just said there, it's black, hits green, and it leaves black again. So it gets changed twice.
Yeah, well, it's all conservative in the sense that there's a green, a black go in, a green and a black come out, whether you like it or not. That's what's going to happen, So if there's two colors in the interaction, there's going to be two colors in the result. It's just that the momentum of the color is going to be different.
Okay.
Thanks
for persisting. No, you had something to say. Go.
No. I think that's complete enough. I'm just saying it is a little bit tricky because, again, it's clear for me to explain the acquisition of acceleration by talking about exchanging polarization, and then it's to explain why the electron doesn't degrade. It's better to explain it as a reflection. I'm just saying, do the two different things. The movement thing is more like momentum exchange, because that's which we understand, right? Fish moving goes in, that adds speed to you, right? So a little fish going the right way, adds to your momentum. So that's really understandable, but that doesn't really happen, so that's the tricky part, is explaining that, you're gaining the fish, but you're only gaining the fish in the sense that you have to move forward to do it. You have to grab a fish in front of you, in a sense. You know what I'm saying? To become part of you, you've added a new piece of polarization in that direction. Well, anyway, I probably made it worse by trying to explain how I'm just saying, for one argument, it suits the explanation to talk about momentum exchanges, where the other part of the argument, it suits the argument to talk about polarization exchanges. But the truth is, polarization is the only thing ever exchanged. There's never a momentum exchange. Fish always go in a straight line forever. And they just change suits. They never turn. They never go anywhere. So every graviton, everything moving through you, is going to keep on going till it gets to wherever the end of the universe is, and then it might reflect off something, who knows. But I'm just saying, everything going through you just keeps going forever. It never turns, and all that happens is while it's going through you, it's wearing some polarization.
Yeah, see, it is confusing because in the one sense you're saying that they will reflect off it at.
Well, I'm saying that's what it looks like in the drawing. I'm just saying you can see the reflection in the drawing, but all you have to do is recognize that that's an illusion of the drawing. See, this tail is green, which should be black, but anyway. So this looks like a reflection. Black reflects, green reflects. But I'm just saying all you have to do is recognize that what's really happening is the black turns green, and then when it leaves, it'll be black again. And the green turns black, and when it leaves, it'll be green again. So I mean, it's saying the arrows are going straight forever, and the only thing being exchanged is their color.
Yeah, well, at least I'm the test subject trying to absorb the information. Maybe when the next person comes along, you'll go, nope, I'm not going to release that statement because it's too confusing, and you're going to be able to refine your argument.
Well, like I said, I don't think I can ever help the fact that it's going to be more understandable as a reflection is going to be more. I mean, it's more visual to do this, right?
Yeah.
Than to have to sit there and draw this green thing turning blue and then going back to being green again. You know what I mean? That's going to be a lot more. It's going to be more challenging for somebody to get the idea of why this blue stays here. It's more easy to say why the blue stays here by seeing it as a reflection.
Yeah, I mean, it's hard to draw these colors, and it is hard to see the colors on the camera. I can't see some of them sometimes, but I'm with you.
Yeah. Yeah.
All right, I'll see if I can get some more questions happening. If I've got any left, I think you've done a pretty good job. Yeah.
I thought you'd ask something. You know, why does maple syrup taste like maple syrup? Yeah.
Yeah. How do the quanta affect Vegemite?
Yeah.
Yeah. See, before you'd made what you just told me, I was going to ask you is, so if you're compressing quanta into an electron, I know it's wrong now because we just had this conversation, but when they go through the membrane of an electron, I was wondering if some of those quanta that get stuck in there get excreted, and it sounds like what you were just saying is the jiggling up and down. When some of those quanta, so it's jiggling and it comes out, it misses the jiggle spot and it can't come back into the compression zone, if that's fair enough to say.
Right. You know, every time it jiggles, it's always releasing blue. You know what I mean? Blue comes into the, as I've tried to explain before, the field still has blue in it, but I'll use it as green just to make it clear that whatever blue's in the field is always equal on all sides. So it's sort of irrelevant to an argument about field changes. Field changes are always going to be about the fact that there's more blue coming in one direction. You know what I mean? There's always, you always have to look for the imbalance. And so I didn't draw the balance because there's actually blue still in the gravity. But I'm just saying that, you know, it'll be irrelevant because the blue one that comes this way will always be compensated by another blue one that comes this way eventually. So eventually it's always going to balance out to being a wobble in this area. It'll always come back to this default because the laws of probability are, you know what I mean? The laws of probability. You know, you can be a head ahead and then you'll be two tails behind, and then you'll be two tails ahead and then you'll be two tails behind. But you're always going to be stuck with coming back to this.
It equalizes
You'll
out.
always come back to this center of gravity. So you're always stuck with that center point as your default until something unbalances the field, till a proton gets close enough to fuck up your field energy. And now you have an imbalance, and now you'll move more in one direction than another direction because there's a clear imbalance in the number of blue.
Yeah.
Okay, so
I'm with you.
That's what I extracted from this image. So you're constantly producing a little bit of EMF as an electron. You know, even when you're not technically moving in a direction, you're always accelerating in all directions. You know what I'm saying? You're going up and down, you're doing all this stuff. So you're constantly losing a little bit of EMF, but it's a little bit. And it's only when you move decidedly in a direction that there's a big boost in how much EMF you release. But like I said, what you're releasing really is this electron. It moves, and the perpendicular dimensions aren't keeping up. So they're just flying out because this left the building.
Yeah, I've seen I was actually watching one of your videos yesterday where you had exactly that drawing. It was pretty simple. It was just 4 sticks.
Right.
And when it travels, you were talking about it gets thinner.
Yeah.
And yeah, the stuff on the sides is basically getting sort of released.
Yeah, it's no longer close enough to the clump to stay in the clump. So it's getting, and once it's free, then it won't have, you know what I'm saying? You'll still be going back and forth in empty space theoretically for a while, but eventually it's just going to be more chaos in a field of chaos.
Yeah.
I mean, it gets a little. The only catch to what I just said, just to be honest, is that you do have to account for that part. Why matter seems different than force on force. Forces don't reflect or bounce off of force. You know, they go straight through all the time. And you know what I'm saying? Like magnetism adds, it doesn't like bend each other. You know, one magnet doesn't bend the field energy coming off another. One light bulb doesn't bend the light coming off another light. You know, I can't put 2 lights next to each other and then get a bunch of light in the middle bouncing off, you know, from the 2 beams of light hitting each other. And obviously in matter, something like that is happening. You know, matter makes it possible for these interactions, these exchanges to take place where they don't seem to happen in the open field. So I haven't quite got that nailed down.
Yeah, well, at least I'm glad that you say that you haven't got it nailed. So basically, when photons are heading straight at each other, do you think they're going through, or do you think? So it sounds like photons.
They have to be inert to each other, but photons make it a little tricky because then you're talking about a frequency exchange, and frequency is a lot easier to understand how that can be exchanged. You know what I mean? Like you can kind of think about the idea that the frequency is separate from these individual exchanges because the frequency is about the state of 2 conditions. So even if I change both the tons and from blue polarization to red polarization, they're still at the same frequency. You know what I mean? Their distance from each other is still the same. So the frequency between them of same polarization, it remains. If you get what I'm saying. So even if I change their color through interactions, their distance from each other is the same.
Yeah, hang on.
Well, I just mean that a frequency can be transmitted even though the thing that was carrying them was annihilated. The frequency can be understood to still carry on. Let me see how, I don't know what a good analogy would be, but it's like if you had a traffic accident and you had Mack truck, car, Mack truck, car, Mack truck, car. You can kind of understand that you'd be able to still see on the residue, you know, whatever came out of that car accident, you'd still see the pattern of car, Mack truck, you know, because the impacts would be still retained. You'd retain the distinction. So I'm just saying the distinction would still pass through the interaction.
Have some of your cigarette.
I'm working on it.
I think, okay, so the problem I've got, if we shine two torch lights at each other, the photons that come out of torch A do not strike the photons coming out of torch B.
I don't think they do, but I'm just saying that theoretically, I haven't quite got this now. Like I said, that's why I'm saying that field energy might be reflecting, but I still don't see how that wouldn't end up creating a bunch of stuff that gets caught. You know what I mean? That starts doing, like, polarization would end up bouncing around in empty space, going back and forth. And I'm just wondering, like, can you really do that? Can you create a electron in the middle of space. And it seems kind of obvious that you can't create those small tons. You know what I mean? You can't create like a half of an electron. Well, maybe you can with quarks. So, a third of an electron. I'm just thinking there's a distinction between matter and field energy. So what I'm arguing is field energy does not interact. So what I'm basically saying is if it hits each other, it doesn't exchange anything. It passes through.
So photons are field energy because they're not...
Right. Anything mobile is field energy. I mean, anything moving in one dimension is field energy, the speed of light. So gravity, magnetism, and photons would all, radiation, radio waves, all that stuff is photons, let's say. But I'm just saying that any radiation moving the speed of light is one-dimensional stuff, field energy, what I would call field energy. So anything moving the speed of light in one dimension is field energy.
Yep, that's all right. So hang on. When you freeze a magnet, are you slowing the quanta down?
Well, freezing is removing polarization noise. So in a sense, what you're doing is you're taking out, like when I showed you the picture of the green stuff and I said there was blue in there, you're preventing maybe the blue. You know what I mean? It's not filtering as much. So you're removing the filtering process. I'm just trying to think of some way to describe this lack of movement, because everything starts to slow down. So you're not accelerating things anymore. So obviously there's not as much imbalances being created. So somehow you're eliminating the field imbalances by taking noise out of the system, if I can say it that way. Like noise would be the random blue stuff that's making that electron jiggle, right? So you're getting rid of the random blue stuff that's making the electron jiggle, if that's a way I can say it. So
that's all right.
Yeah, so you're sort of creating a lack of density of blue. So you're collecting the blue polarization from the field. So you're doing that by either creating where you're sucking out all the atomic particles. So all the atoms that would be emitting blue, you're pulling them out of the environment. You know what I mean? Like a vacuum, and so you're trying to get as much noise out of the system. So yeah, so you're creating an insulated shell where you pulled all the atoms out, like a vacuum sealed vessel. Okay, like there's no vacuum on the inside. You know, like where they store liquid nitrogen or something. But the vacuum that it's sealed by a vacuum, where the vacuum is preventing atoms really from moving, right? So that's what a vacuum really does. A vacuum bottle, it's really preventing atoms from getting through. It's not preventing electrons, but it's preventing atoms from moving, migrating. And so that's preventing the atoms from emitting these blue bits, because now the blue bits can't get across the vacuum, if you get what I mean. They have no electrons to exchange with, so the blue bits don't go anywhere.
Yeah, so it's just cleaning up. It's cleaning up.
They're being pre-filtered. So that's why they can do that with like a vacuum or magnetism or, different field modalities. They just put a field around it essentially, and that field will filter out all the extra little blue and red bits, because it's the blue and red bits that keep the electrons and the neutrons vibrating. So the less blue and red bits, the less the neutrons and the electrons vibrate.
Okay, so when you heat a magnet, right, it creates an environment where these quanta and protons and electrons can just move in all random.
Well, it's not exactly random, but yes, they're just now twice. It's more the more blue and red you put into their environment, the more jiggling they're doing. So now their space between them has to be bigger because they're moving in broader circles, right? So they're saying, I hate you in a wider area. So it's almost like their territory is increased. You know what I mean?
Yeah.
Because their repulsive energy is still going to be strong. So they're like a dog who could be defending a 6-foot territory, and then he decides to defend a 12-foot diameter territory. And so everything's getting bigger and producing more angriness. Okay, whatever you want to call it, you know what I mean? Hostile energy. So it's just you're inciting a more an expansive environment in that everything is being obliged to use more space, and that's really what the end result is most things expand when you put heat in.
Okay.
That's why they're expanding, I guess. I'm just trying to give you an explanation for why the expansion takes place. It's because the excitement obliges there to be an expansion of space because the dogs are angrier. If I can say it that way.
You can say whatever you like.
Well, I'm just trying to make it understandable.
Yeah. Well, there's no book to go to, is there?
Well, there are books, but I just mean, yeah, they're not going to. Their answer is going to be virtual photons do blah 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 and cause blah blah, and then that makes this move faster. You know,
Yeah.
they're going to leave out an awful lot of pieces. So I think my explanation is going to have more pieces in it. You know.
Yeah. Well,
they'll say the bent space bends, and that causes the matter to move. You know.
Yeah. I think I probably about done.
Well, good. I think maybe yes. It's probably a good enough whack at it.
Have you had? Oh, obviously we didn't have any interlopers because you didn't post the link, right? So, is there any questions in the room?
Yeah, there's not. Let's see. You've been gone a while. Let me see. There hasn't been much. I mean, I wasn't watching it, but I can read some of it here. Let's see what we got. I don't know. People sending kisses and such. AC voltage. That's an old. Perhaps should use the word gravity to describe the fundamental field energy you speak of. Gravity will unlikely lose its connotation to the macro observation of attraction. You know, I don't know. I mean, you know, this whole argument about how to describe these quantons, but I mean, the truth is that the fact that Einstein took gravity out of physics is a real problem for physics because, frankly, magnetism is a byproduct of gravity. That's where the energy comes from. That's why they don't have an explanation for the energy that's obvious in magnetism. I mean, it's obvious in the sense that, yes, it's not movement of matter, but it is a field energy that's produced much like light. You know, it's a radiation. And yes, not everything's vulnerable to the radiation, but it would be silly for you to say that a light bulb isn't energetic. Magnets are energetic, and their energy is it's making gravity, it's manifesting gravity in a new form, and that new form is just as energetic as the radiation coming off of a light bulb. I mean, to matter that can see it. Obviously, I mean, light goes right through some things, right? I mean, I can have ultraviolet light go right through some things and be totally blocked by other things. Like ultraviolet light is blocked by glass. You know, generally speaking, I mean, glass is opaque to ultraviolet light, and so I mean, obviously, it depends on whether the thing it hits is sensitive to it, whether it's a bit of energy. But I'm still going to argue that understanding that, I mean, I can't really take gravity out of the conversation because gravity is the source. Okay, it is the thing that really makes the little arrows, and any light you see or any magnetism you see, those things are really just tagged gravity. They're just gravity wearing the damn suit.
So magnets are just focusing gravity to a localized point.
It's not really focusing it, but it's changing the percentage of the arrows that are wearing suits. If you can think of it that way, it's consolidating suit wearing.
In a localized spot.
Yeah,
right?
It's segregating it. I don't know how to say it, but yeah, it's making all the stuff wearing red suits go out the red end, and it's making all the stuff wearing blue suits go out the blue end. So it's diverting the suits to the two poles of the magnet. So all the red suits go out the red end, and all the blue suits go out the blue end. and there's very little crossover. So you have this pure filtering of the polarization. So all the blue poles go out the blue, all the red poles go out the red, tend to the red end, and yeah, that's the nature of the filter.
Yeah, that's why when we first started this session, I asked if you'd draw the north and south and the north interaction. So one thing
I
that
sort
you
of have a picture on the website. There's the the main drawing has a somewhat a drawing of that on the website if you look at it. But it's down towards the bottom where I get into the magnetism stuff. But yeah, I still got to rewrite all of that, unfortunately. Anyway.
I think you've got lots of writing to do. This is going to be, I mean, it's obviously.
Yeah, I want to do the minimum amount. I just want to get this over with. Anyway, there was an old science fiction book about that, having no gravity in the center of the hollow earth. Very interesting concept. Yeah, well, it's just that you've restored balance. So again, you only feel gravity or see gravity when there's imbalance. So when you put an equal amount of mass on both sides of you, you will think you haven't changed anything because you're back to equilibrium. I mean, clearly you're going to be in a different environment when you have a ton of matter on both sides of you. But from a gravitational point of view, you've neutralized the imbalance, and imbalance is the only thing you can detect. All right, what happened in Mendham? You were a lot more Zen back in 2009. I was never Zen, so I don't even know what that means, you fucking cunt.
Hey, on that note, I'm going to leave you to enjoy your comments in the room.
Okay.
Thanks again for putting up with my questions. And I'll speak to you sometime soon.
Okay, so yeah, just let me know on Skype. Like I said, if there's a time you have, it's good for you. If you say 5 hours from now, you'll be available for an hour or two, then I can always make a room.
Sure.
But yeah, it always has to be kind of at the moment notice. Usually, I'm not going to notice at the moment notice. Are you there? Like, are you there? Stuff doesn't really usually. I'm not there. Usually, at the time somebody says, "Are you there?" I'm usually not there.
Yeah, unfortunately, I probably can't do any better than that. And if you've got things to do, you just do it. And if you can, I probably can't get any better than "Are you there?"
Well, I'm just saying, if you know an hour ahead or 2 hours, that would be fine. Just to post a thing saying if you're available an hour from now, then that'll be fine. And if I respond, then you'll know. And if I don't, then you'll know I'm distracted or busy or some other bullshit. But Oakley,
that's okay. No problem. Thanks again, Gary, and I'll see you soon, mate.
Okay, take care, and don't be too Australian. Okay.
I'm not an Australian. I'm just a person that lives in that region.
You all try to say stuff like that, but I'm not fooled.
We're just monkeys in different taxable regions.
Yeah. Except you're living like on a lead-covered island or something. Quite obviously, it's not a lot of lead and other brain-destroying chemicals over there in Australia.
Yeah, we're all licking windowsill paint.
No, I'm just saying there's something going on. I'm just saying, okay, whatever it is, koala shit has lead in it. Something. There's some truth. They'll find the underlying mutant bug that exists in Australia, and they'll figure out why.
All of those koalas are actually stoned on eucalyptus.
Well, exactly. So I think it's in your water and everywhere else. I think you're all a bit of a fucking loopy-doo. But anyway, keep trying anyway.
Bye.
Someday you might grow up to be a real person living on a real continent. Someday.
Oh my God.
Yeah, someday.
It's a prison island. I'm not allowed off.
I'm just saying, someday you might, get to do this, be a serious Earthling. But okay, keep trying.
See you later.
Yeah.
Bye.
Bye. All right, show Fitch picture again. No, he's not doing that. This producing at least a little bit of radiation. Thus producing at least a little. It seems that more natural than electron must be moving at least some. Yes. Yeah, they are moving. Some. I was thinking of that too. It seems incorrect that they teach an electron is static and only produces a photon when accelerating. Yeah. Well, they are accelerating. I'm just saying that just as we're accelerating on the Earth, we don't look like we're accelerating. But you really are moving down at 10 meters per second, and then you move back up at 10 meters per second, and then you move back down, and then you move back up. So this is what you're really, the path your atoms are traveling is this a lot of travel. That's why actually the clocks on the satellites have to be sped up, is because you're the one being time dilated, because you're moving so much faster than the clocks are, because you're going up and down. So to do all that distance, you have to go a lot faster than we look like we're moving. See, we look like we're just moving as fast as the Earth is spinning, but we're moving a lot faster than that because we're doing all this goddamn up and down shit. All right, can you show the diagram again? I don't know what diagram it was, but no. Perhaps should not use the word gravity. Yeah, we did that one. Let's see if there's anything else here I missed. All right, well, anyway, yeah, so Mockingbird guy. I was never Zen. I was thinking of that too. It seems incorrect that they teach electronic static. Okay, yeah, so we did that. All right, yeah, so we're done. All right, so I can go soon. Like now. But anyway, yeah, so I have been distracted by things. I always getting myself into all these projects, and so I've been thinking about doing this other, debate forum thing, working on a better debate forum on the internet and all that kind of shit. So it's, sucking up a little more time. And yeah, the key thing was just doing this. I had to figure out again the mechanics of the arrows. I just want to be sure of them so I can put them into my model, the programmed model. And so now that I know better what I'm looking to try to do here, I think I can advance that, and without having I just hadn't got the formula right. So obviously the model wasn't working because it's very exact. Like I said, you get this a little bit off and it all goes to hell. So it's almost like playing with nuclear bombs or something in terms of the model. You really have to be strict about the rules you create, or the model gets unrecognizable real quickly. Tiny little mistake made. It's almost like compressing graphics or something. You break the rule of the compression a little tiny bit and you won't even be able to tell what the image was. And it's only a tiny error being made. So it doesn't take much of an error to fuck the whole thing up. So I'm not making, I do tend to make excuses for my sometimes less than magnificent productivity. But yeah, I am, doing the best I can, and I guess that's all can be said. And maybe the best I can needs to be better somehow. So I must find a can of better canning and drink it. Yeah. I need some blue arrows to hit me. Give me a little more. Go, Gary, go. Something like that. Right. So for anybody who's watching this that may be interested in joining the room, you just got to post a comment, or comment when the live room is running or something, just to acknowledge, say that you would like to participate, and I can send you the link, and you can let me know what times are good for you if you have something you would like to argue or defend in terms of classic physics. That's sort of what I'm looking for, is defenders of a classic model. And such. Yeah, it's just I won't post the link public anymore because that just doesn't work. So anyway, what is the room? Well, the room is in here where I am, and where the guy you just listened to, the Michael guy, was. That's the room. And if you have a webcam and a microphone, you can come into the room and actually talk in the room. You see? Yeah, that's what the room is. Yeah. I guess I should call it the room. I could draw room on it or something. I don't know. Have a little sign here. This is the room here. Yeah, it's a virtual room. It's like not a real room. It's a virtual room that we are transported to through photonic technology. I should have come to this earlier. I don't know what that means exactly. Yeah. But I don't understand people too often, so it's okay. I should have come to this earlier. I don't know what that means. I imagine there'll be more of this coming soon. So you'll be able to get to more of this in the future. So no worries. To this page. I don't know, this page. Yeah, well, I mean, the place you're typing at right now, that page won't exist shortly. Yeah, yeah. Well, the DraftScience is a channel, so it's not really a page, but okay. Yes, it's a YouTube channel, and these rooms are recorded for the benefit of the posterity. So they are live until they are no longer live anymore. And then they're recording. I probably should change the name of the dead rooms. Yes. But there's so much to do that I'm not going to do that because, I got shit to do. I don't got time to be fucking changing the titles of videos. Let's see. What are you going to do? Oh, I don't know what that means. I'm going to leave the room soon because it's late and I'm tired. And then I will make another room in a day or two, and then I will close that room, and then I'll make a room in a day or two, and I'll just keep doing this until I'm dead, or something close to dead. Apparently, that's how it works. Are you going to do the same thing in rooms only? Are you going to do the same thing in the rooms only? Yeah, so this is the DraftScience channel. So we just do this draft physics things because I have this unification theory that I'm attempting to sell to the universe. But I do make videos on, I have a channel called In Mendum. Well, you can go to donotgod.com and there's links there, I think. Well, anyway, the amendum video is on a sidebar there anyway. Because spelling in mendum will just get you into trouble. But it's in mendum. So anyway, so if you go to that channel, then there's lots of fun things to do. Yeah, I typed on it. It's not working. So if you go to in mendum on YouTube, you will find the philosophy channel. So there I do philosophy. But anyway, very uncheerful philosophy. Yeah, all doomed and life is stupid. Well, it does make science more sciencey. Yeah, I've really sort of enjoyed this little project just because I was so irritated by how cognitively incomprehensible physics was, and I really like the idea of physics. I mean, I like the idea of having a mechanism, and understanding it, and I really hated that it was so wacky with all this. Heisenberg and stuff and all this uncertainty shit and all this bibble babble bent space crap and time warping, and it was just so irritating. So now I just feel so much better having a vision of physics that's just so simple and just so logical. Crap goes in, crap goes out. No bullshit, no uncertainty, no Tinkerbell, no leprechauns. No bullshit. So, anyway, where was I? Leaving. That's what I was doing. Leaving. Let's see. How long have I been doing this anyway? I don't remember when I started. It used to tell me somewhere. Yeah, it used to say somewhere how long the room's been open. Huh. Started streaming 2 hours ago. Oh, that's just kind of a vague statement. But anyway, that is probably enough 2 hours. Yeah. Don't want to make this video too much big. Anyway. Yeah, that's what it says here. I mean, usually it says there's a place somewhere, I think, where it says the exact hours and minutes, but at the moment I can't find that. You and that Michael guy are really great together. Very enjoyable watching. Yeah, I don't know where exactly. It's kind of like, you know, I don't know. It's like me and you is like Abbott and Costello, you know. But like me and Michael is like, I don't know. Frog and salamander. I don't know. Well, it's probably I could just compare it to sleepy kitten and dopey koala bear. Well, anyway. No, but I mean, we are able to communicate with each other, which is good. And he can take a joke a little bit. And what else is good? Yeah. Yeah, what was I going to say? So something I was going to say, but I can't remember what it was. Yeah, I don't know. Yeah, I'm kind of, you know, I tend to like somebody I can insult more, but you know, too bad. You know, I'm good with everybody though, right? I mean, look, I mean, seriously, anybody who's a little bit reasonable, I'm a very nice person, a very good communicator. There's been very few people I've ever had an interaction with, you know, that was trying to anyone who was trying to be the least bit serious that I've ever had a problem with. I'm really good at communicating with people, I think. You know, as much as I don't seem to have any native feeling for it or any native, you know, I mean, I don't like people generally speaking, and I just, you know, I always feel a little bit awkward dealing with people. Once I do it, I'm pretty natural, but it is kind of funny that I really don't, you know, I don't naturally gravitate to it. I'm very introverted. Yeah, you know, I'm probably, yeah, I like explaining. I like dissecting. So I like talking about mechanics. So I guess that's really what I'm doing. I'm just listening. I'm just hearing him tell me a problem, and then I'm solving the problem. So it's like I'm not really talking to him, which is sort of rude, I guess, in a way. I'm just, you know, I'm just letting him read questions like he was the computer reading questions. So, but I mean, I think I am. I mean, I think we do personally get each other. So I think it is a, you know, a friendly enough thing. Yeah, I don't want to diminish the social quality of it. I just mean that I'm just not a very, you know, I'm socially inept or socially retarded. Socially autistic. Yes, socially. Let's see what other. We see if we can come up with some other French fry word or something. You just keep coming up with silly words for stuff. Anyway, that's probably enough now. Now it's probably enough. Probably time to say goodnight. So good luck in New York there, old fan, and don't get damaged. Terribly messy, dangerous place. And what else? I don't think there's anything that's urgent. Yeah, I'm just so, you know, I see, you can see it in my eyes. My eyes are fading. This time of year, I always have a real problem with this. You know, when the seasons change, it always fucks me up. My whole biochemical thing just completely goes to hell. Yeah, well, I sleep pretty well, but yeah, I've been dreaming way too much lately. So it's like some nights I wake up, you know, some mornings I get up and I'm like, oh, I'm exhausted. You know, it's just like digging ditches all night in my dreams or something. It's like it's just very, yeah, it just seems like being, it's a, you know what I mean? It's like, it's kind of like going to work sometimes. I mean, dreams are very, yeah, they can feel like work. And such. So anyway, okay. So now I think now I'm ready. I think my hand is ready to go to the mouse and move it to the button, the lovely reddish button. It's a little bit orange, but we can think of it as red. It's not round; it's square, but that's probably okay. It's right next to the word live, and I get to turn the live off. Yes, so that'll be nice. Yes, they ought to call it, instead of stop broadcasting, stop being alive. Yeah, stop living. Yes. Yes, well, I am probably, it's probably one of my relatives did actually have sex with a lizard or something. So I do sometimes feel kind of like I'm a cold-blooded animal, and I really should just hibernate through the winter. I'm thankful you're like a guy from I Am Legend. Oh dear, it's a beacon of hope. I Am Legend. That movie was weird. I have a physics question though. Oh, okay, we'll get to it. Either ask it now or save it for later, but go ahead. Physics question. Get to it. Fast, fast, fast. Move, move, move. Type, type, type. Oh dear, not the harp thing. Yeah, well, the harp thing is just, look, you can send vibrations through anything if you make a big enough noise, right? I mean, a nuclear bomb technically creates a seismic disturbance that bounces all through the earth, and that's how we detect when the North Koreans have done one and all that kind of stuff. So it's not like you can't send vibrations, sonar, almost, you could call it kind of sonar, I guess. But yeah, I don't really go for all this. You're going to be able to use it instrumentally in any way to actually do anything on purpose. So you might cause an earthquake, you might not. I don't, yeah, I just don't think, it's like people dying of a heart attack shoveling snow. It's like they were going to die of a heart attack anyway. Okay, the snow didn't kill them. Their, you know, greasy heart killed them. And, you know, if HAARP's going to cause an earthquake, you know, it's probably an earthquake's going to happen anyway. So it might be doing you a favor, because instead of having a big earthquake 10 years from now, you only have a little one now. So harping might be a good thing to do. But anyway, do you have a specific question regarding harp? I don't even know what it stands for. High amplitude aerial repercussion. No, that wouldn't work. Holy Apple Annie regurgitation placenta. No, that wouldn't work either. Well, I don't think they're attempting to do anything, but you know, I'm just saying it's kind of like, look, Tesla was the guy who first kind of accidentally fell on it, in the sense that he took, you know, very high voltages and just drilled a ton of electricity into the ground, and yeah, that'll, you know, shakes the earth. You know, But I don't, like I said, I don't know if there is any real purpose to it. I mean, I don't see any real function myself. I just don't think it means anything. I mean, there's people who think you can change the weather or you can do stuff, and I just don't think you can do anything meaningful. Well, they're attempting, like I said, it'd be kind of convenient to be able to communicate with, let's say, a submarine, right? Like it's really hard to send radio to a submarine unless it lets a little buoy up that makes a bunch of noise that the enemy can find. So it'd be really cool if you could just send signals through the earth and they were omnidirectional in the sense that you really couldn't tell what direction they came from or anything. And so you could send a bunch of, coded messages into the earth. The submarine could receive them, and then it could do some blip blip back that you might be able to get back. But it's unlikely that the submarine could create enough disturbance to be audible from any distance. But I'm just saying you could definitely send one-way signals to a submarine, let's say, using HARP. Well, I mean, you can change the weather. I mean, I'm just saying that it depends on how much you're going to change it, right? I mean, you could change it a little tiny bit by just shooting some salt into the, take one of those flare guns or something, shoot a little blob of, whatever. I don't know what the chemicals are, but even dry ice will work to some extent. So you can create a little bit of weather, so make little changes. So anyway, so I guess your questions are more of a general nature than I was looking for. Very good, though. So I still think I'm done now then. HARP isn't very important, in my opinion. Not very interesting technology. It's just, in my opinion, it's just not worth much attention for my brain that must prioritize and such. So anyway, thank you though. It's good to have participants participate, and I will see you. Who knows? Tomorrow, next day, who knows when? Something like that though. In a future. I guess I would be implying there's more than one, but yes, there are sort of futures that are soon to be futures and then futures that are long futures away. But I'm just saying, yes, somewhere in the future, I'll see you. Yeah, that's it. Yes, well, now they're dated, but yeah, obviously there's some times when I seem to do them daily, but there's other times where, like I said, I hadn't done one in a few days. So it just depends on whether I have something to talk about or not. The Ken guy did make a video on light, but it was just, he didn't even say anything in the video. He just calling people morons. And it's like, well, there's just no value in making a counter argument because he just says stupid things like, a wave in what? And then I want to say to him, a perturbation in what? Coaxial cable made of what? I mean, light's like a coaxial cable. Oh, yeah, that explains it. Sure, just like it. You can see the cables, obviously. When the lights are on, it's all those cables are all, holy shit, look, I mean, just waving, all these cables are in the way. It doesn't make any sense. So anyway, yeah, I might as well just throw a Ken insult in the end here. Ken Wheeler is a despicable, pontificating lard-mouth. Yeah. Of low integrity. Yeah. Very small man in a very big fat body. Yeah. Yes. Yeah, I wouldn't dispute his knowledge of cameras. I mean, he went to photographer school and such, and he has been spending years playing around with this stuff. So he definitely has some knowledge. But I don't even know if his knowledge is, as technical as would be useful, in the sense that I don't know whether he knows the difference between a convex and a concave lens. But he clearly has used lenses from all over the world because he apparently has zillions of dollars with which to buy all this crap. But frankly, I just, when I, like I said, I looked up a couple of these lenses. People actually pay $3,000 for a fucking lens, and you're just like, huh? Who's got that kind of money to throw away on lenses, for fuck's sake? And apparently, the real value of these lenses is the artifacts that they create. It's not like they actually take a picture of the thing, it's a good picture of the thing you're taking a picture of. The real value of the lens is it creates a bunch of shit in the background. So it's like, how much distortion, how much real image can you get, and then it fucks everything up totally. So it's like, I mean, I'm not saying that isn't an interesting effect, but it's not really, I mean, to me, not getting false pixels shouldn't be the real game of photography. Is the real game is to get as many accurate pixels as possible, and then fuck them up, in Photoshop or something. But you'd think you'd want to get the raw thing as accurate as possible. I would anyway. I mean, having the lens fuck it up for you, I don't know. I mean, I suppose it works, like I said, because you got the aperture open enough, and you take a long enough exposure, then you can have this really tight focal length. So only the plane of my face will be in focus, and everything else will be totally fucked, and that is a nice effect. But $3,000, I ain't gonna pay $3,000 for it. But anyway, enough of that. Yeah, I'm just saying it's just, even for professionals, I'm just saying, I just don't, I'm just not sure I buy that all of this is, you need $3,000 lenses to do a professional job. That's all. I'm just not sure you need that. But anyway, yeah, and such. I like my good old $10 cameras. $10 broken camera. I take one every day. So anyway, till the next time, and such and so forth and whatnot. And yeah, that's enough. Pretty sure.